In this video, I will go over the answers to the 2023 Unit 3 Practical Booklet B. So on to question 1. This question incorporates material from year 11, or what you did in Form 4. So this is Unit 1 material. Name solution A. Okay, so let's look at what test 1 is. A few drops of solution A were added to a solution of sodium chloride. There's a white precipitate formed. Well, this is not testing for the sodium ion, it's testing for a chloride ion. And chlorides, bromides, iodides are all identified using silver nitrate solution. So solution A must be silver nitrate solution. I don't actually need to put in the word solution here because it's given to us in the question. If it hadn't have been there, if it just had have said name A, then you would have said silver nitrate solution. For part 2, write the formula of the white precipitate in test 1. Well, when the silver nitrate solution is added, it's the silver ions which react. They're Ag+, and they react with the chloride ions. They're Cl-. And when those two ions come together, it just forms a white precipitate. Okay, it's insoluble. So silver chloride is the white precipitate. Name liquid B. So again, let's look at what it says. It's a flame test, and the nichrome wire is dipped into liquid B and then into the sample. Well, liquid B is going to be concentrated hydrochloric acid. Part 4, what would be observed when test 2 is carried out? Well, test 2 is going to identify the sodium ion, and sodium ions produce a yellow or an orange flame. I'm just going to look at test 3 because it's needed for the next question. Universal indicator paper is used and it changes to green. So let's look at the next part of the question. State the pH of the sodium chloride solution. Well, that's obviously going to be 7. And part 6, what colour would be observed when sodium chloride solution is tested using red litmus and blue litmus? Well, it's not going to change the colours of these indicator papers because it's neutral. So red litmus will just remain red and blue litmus will remain blue. Part B, we've got a white solid, it's thought to be zinc sulfate. Describe tests you would carry out to fully identify the solid as zinc sulfate. So we're thinking of tests that will identify the zinc part and the sulfate part. So we've got to make sure we include the reagents and then what observations we would have. So let's do the zinc ion to start with. And I'm just doing bullet points. In chemistry, we love bullet points. Now, the first thing you've got to notice here is that it's a solid. And to carry out these tests, we'll have to make up a solution. So that's the first thing we're going to do, make a solution of the compound. Now, if you think back to doing this test, there are two solutions which are added to identify certain metal ions. There's sodium hydroxide solution and ammonia solution. Now, in this case, it is ammonia solution. So I'm just going to focus on that for a moment. So I'm going to add ammonia solution, and it will form a white precipitate. Now, if the ammonia solution is added until it's in excess, that precipitate disappears. Now, just to make a point here, why can sodium hydroxide not be used? Well, if sodium hydroxide is used, it will produce a white precipitate with zinc ions, just the same way as ammonia did. It would also produce a white precipitate with aluminium ions. However, if the sodium hydroxide solution was added until it was in excess, then both precipitates, those caused by the zinc ions and those caused by the aluminium ions, would dissolve. So hopefully you understand that. So with sodium hydroxide solution, you will get white precipitates with zinc and aluminium solutions, but both of those precipitates will then dissolve, so it can't actually distinguish between zinc and aluminium ions. Whereas ammonia solution does produce a white precipitate with the zinc and the aluminium ions. However, only the precipitate formed from the zinc ions will actually dissolve, so the aluminium precipitate remains. So hopefully that's clear. So now I'm going to test for the sulfate ion. And again, I'm using bullet points. It makes it nice and clear, and it makes it easy for the examiner to mark as well. Well, the solution we used for sulfate ions is barium chloride solution. And when it reacts with a sulfate, a white precipitate is formed. So if you've got 5 or 6 of those points, and you just get 6 marks. Question 2 says for the decomposition of hydrogen peroxide. So A part 1, name the catalyst used for this reaction. Well, manganese dioxide is the catalyst used, or you can say manganese 4 oxide. Now be careful that you don't write something like manganese 4 dioxide. Okay, that would be wrong. Now we still have to describe its appearance. Well, it is a black solid. What is meant by the term catalyst? Well, this is a substance which increases the rate of a reaction without being used up. On to part B. So we've got the apparatus below, which is used to monitor the mass during the catalytic decomposition of the hydrogen peroxide solution. So part 1, explain why the results obtained from the experiment are more reliable when a cotton wool plug is placed in the top of the conical flask. Well, when the hydrogen peroxide decomposes, you actually see lots of bubbles, and some of the liquid could actually escape from the conical flask if the cotton wool wasn't there. So the cotton wool prevents loss of liquid, and if liquid was being lost, that would obviously affect the mass readings. Part 2, what piece of apparatus is missing from the diagram? Well, if you look up at the top, it says that the decomposition of the hydrogen peroxide solution was monitored over a period of time. That indicates that a stop clock is needed. Or you can say a stopwatch, not just a clock. You don't say a clock. Okay, then part C, we've got results of the experiment. And part 1 is asking us to explain why the graph leveled off. Well, remember, the hydrogen peroxide decomposes into oxygen and water. The oxygen is a gas. And the reason it levels off is because the reaction is complete, or there's no more gas given off. Part 2. Calculate the mass of oxygen lost during the experiment. Okay, well, you're just looking at the original value, which is 125.25. That's a 5. And you're subtracting the final mass, which is here, and that is 125.01. That's 0.24 grams. Part 3. So here we have to calculate the concentration of the hydrogen peroxide using the mass of the oxygen that was just calculated. So let's see, that then was 0.24 grams, just to remind us. So the first thing I'm going to do is work out the number of moles of oxygen. So that's going to be 0.24 over the RFM, or the MR of oxygen. That is 32. That's 0.0075. Now look at the ratio. It's a 1 to 2. Therefore, we're going to have double the number of moles of the hydrogen peroxide, just 0.015. This can now be converted to a concentration using the volume. So that's why you've been given the volume here. So remember, concentration equals moles, which is 0.015, over volume, which is 25. Now this is in cubic centimetres. So we're going to multiply this by 1,000, and that gives an answer of 0.6 moles per cubic decimetre. And then part 4, sketch the line you would expect to obtain if the experiment was repeated at 40 degrees C, everything else kept the same. Well, the original was carried out at 25 degrees C. So if the experiment is at a higher temperature, you're going to get a faster rate of reaction. But if everything else is kept the same, then it's going to start and finish at the same values. So I'm going to start here. Because it's going to be a faster rate of reaction, it's going to have a steeper gradient, but it will level off at the same place. On to electrolysis, which you would have covered in year 12 or form 5. What is meant by electrolysis? That's just the decomposition of a liquid using electricity. One reason why platinum is used for the electrodes, that's because they are inert. Or you could, I suppose, also say they're very good conductors of electricity. That's another reason why platinum is used, or graphite as well. Explain why dilute sulfuric acid conducts electricity. Well, it contains ions, and the ions are able to move and carry charge. So part 4 then is where we have to complete the table stating what happens at each electrode. Well, the name of electrode 1 is the anode, because you can see here electrode 1 is connected to the positive terminal. So that's the anode. And electrode 2 therefore is going to be the cathode, but again you can see it's connected to the negative one. The product, or the gaseous product of the anode, is going to be oxygen. And the clue is here as well. The half equation for the formation of hydrogen, well, remember this starts off as a hydrogen ion. So that is going to gain an electron to form a hydrogen atom, but it's a diatomic gas. So this reaction happens twice, and then the 2 hydrogen atoms will combine. So in total there will be 2 hydrogen ions, which gain a total of 2 electrons to form H2. Now don't write 2H. 2H means 2 separate hydrogen atoms, whereas H2 means that the 2 atoms are bonded together. It's a diatomic molecule. Part 5, 20 cubic centimetres of hydrogen gas were collected in electrode 2. Predict the volume in electrode 1. Well, for this one, remember, water is H2O. You have twice the moles of hydrogen as you do of oxygen. So if there are 20 cubic centimetres of hydrogen gas, that would indicate that there will be around 10 cubic centimetres of oxygen produced. Okay, on to part B. Describe how you carried out a test to identify ammonia gas. Okay, so this comes under the topic of gas chemistry. And for this, you're going to use a glass rod, or you could use a stopper from a bottle of hydrochloric acid. On to question 4. So we've got a hydrated salt, chromium 3 nitrate, violet solid, All of the water of crystallization may be removed by heating the sample to constant mass. So the first thing you have to do here is draw a labeled diagram of the assembled apparatus used to heat the solid. Well, the container that has to be used here is a crucible. I'm going to draw it. So sometimes an evaporating basin is used for this experiment, but for this particular question, it does specify a crucible. Now, a crucible sits into a pipe clay triangle. Just going to represent it using circles, and that sits on a tripod. It's going to be heated, therefore a Bunsen is required. So we write heat with an arrow, and everything has to be labelled. The sample is going to be in the crucible, and then, as I say, everything must be labelled. There is. You can include a heat-proof mat as well. On to part B. What is meant by water of crystallization? Well, that is water that is chemically bonded into the crystal structure. Part C, heat to constant mass, just means that the sample is weighed, heated, and that is repeated until the mass stays the same, or until you've got two mass measurements that are the same. D, calculate the mass of the crucible and solid obtained if all of the water of crystallization is removed. Well, there are two ways you could do this. So let's look at the first way. Well, if we subtract the 25.24 from 29.24, that will give us the mass of the hydrated salt. So that's 4 grams. This can be converted to moles. That's 0.01. So all I've done here is worked out the MR of this part, and then I've added on 9/18. So the total MR, or RFM, is 400. We've established that there are 0.01 moles of this whole salt. This is the hydrated salt. And you can see there's a ratio of 1 to 9. So if there are 0.01 moles of the hydrated salt, there will be 0.09 moles of water. This can be converted to a mass. So the mass of water is 0.09 times 18, it's just the MR, and that equals 1.62 grams. So now what we can do is subtract this from the mass of the crucible and hydrated salt. That works out to be 27.62. Now there is another way of doing it. The first part of it is the same down to here. We've got 0.01 moles of the hydrated salt. So imagine the hydrated salt, which is this, is heated and decomposes into anhydrous chromium 3 nitrate and water. Okay, so all this equation is showing is our hydrated salt going into the anhydrous salt plus the water, and the 9H2O is coming from here. This gets driven out. I've just calculated that the moles of the hydrated salt 0.01. So that means then that the moles of the anhydrous salt will be 0.01 because it's a 1-to-1 ratio. This here can be converted to a mass. So the mass, 0.01 times 238, and that equals 2.38 grams. The question is, what is the mass of the crucible and the solid after all of the water of crystallization has been removed. So this is the anhydrous solid that it's referring to. So it's the mass of the crucible plus the mass of the anhydrous solid. And when you add 25.25 to 2.38, that equals 27.62. And part E, one reason why the mass calculated may be greater than the mass obtained when the experiment is carried out. Now, this type of question is usually asked in a different way. Typically, if you get a value for water of crystallization that is greater than the expected value, so say this was 11, then that would indicate that some of the salt had decomposed. This question is the same type of thing. So why might the mass calculated in D be greater than the mass obtained when the experiment was carried out? It is likely that some of the solid decomposed. Question 5. So we've got hydrated iron 3 oxide, which is rust, iron nails wrapped in different metals, and the first part of the question is we have to decide if the nail rusts. So, tube 2, the nail is wrapped in silver. Well, there is going to be rust there because the iron is more reactive than the silver, so the iron would react first. So that is going to be yes. Copper, again, that's going to be yes because iron is more reactive than copper, or you could think of it in terms of iron is higher in the reactivity series than copper or silver. For zinc, no, the iron is not going to rust this time because the zinc is more reactive than the iron and it reacts first. Now explain why rust does not form in test 1. Well, in test 1 you can see that magnesium is wrapped around the iron nail, and magnesium is more reactive than the iron. Therefore the magnesium reacts first. It's similar to the zinc situation. Of course, this method of preventing rusting is known as sacrificial protection. Part 3, explain why all the nails in the test tubes would eventually form rust. Well, even the ones wrapped in magnesium or zinc will rust because the metals magnesium and zinc would eventually get used up. Part B, it's quite a long introduction. The first part, write a balanced sum equation for the reaction of iron 3 oxide with sulfuric acid. Okay, well, iron 3 oxide is that. Sulfuric is H2SO4. That's going to form iron 3 sulfate. So the 3 goes after the sulfate, and then the 2 goes after the Fe. And water. I can see that there are 3 sulfates on the right, so I'm going to need 3 SO4s on the left. And then I need to balance the hydrogens by putting a 3 on the right. Part 2, another balanced sum equation, the reaction of iron 2 sulfate with iron. Okay, so that's going to be Fe2 SO4 3 plus iron, and then that goes to give iron 2 sulfate. You can see that there are a total of 3 irons here on the left and 3 sulfates. So a 3 on the right hand side balances that up. Identify the green precipitate. Okay, so let's look at what's happening here. So we've got iron nail, excess sulfuric acid, changes from yellow due to the formation of iron 3 sulfate, and then changes to green as iron 2 sulfate forms. When iron reacts with the iron 3 sulfate, the resulting solution is then placed into separate test tubes. Sodium hydroxide solution is added. So remember, sodium hydroxide solution is used to identify certain metal ions. One of the test tubes forms a green precipitate. Well, that identifies iron 2. Iron 3 would form a brown precipitate. So the green precipitate here is iron 2 hydroxide. So I'm just going to write an ionic equation for that. So we've got our iron 2, that's the green solution. It reacts with hydroxide ions from the sodium hydroxide solution to form a green precipitate of iron 2 hydroxide. Suggest why the green precipitate does not form until 6 cubic centimeters of the sodium hydroxide solution were added. If you look at the question and try and understand what's happening, the iron nail is in sulfuric acid. So there's still going to be sulfuric acid here whenever the solution is filtered and put into separate test tubes. The reason the green precipitate doesn't form at the start is that the sodium hydroxide solution that's added initially will just react with the sulfuric acid. And then once all of the sulfuric acid gets used up, the hydroxide ions will then be able to react with the iron 2 ions. So come back to the question. Why does the green precipitate not form until 6 cubic centimeters of sodium hydroxide solution were added? That's because the sodium hydroxide is neutralized by the acid. Or you could say the sodium hydroxide reacts with the acid. Name the gas causing effervescence in the second test tube. So let's look at what it actually says in the question. Solid sodium hydrogen carbonate is added to the second test tube until effervescence stops. And then a piece of magnesium is placed in the test tube. Well, hydrogen carbonate and carbonates always produce carbon dioxide gas. And part 6, what will be observed when magnesium is added to the green solution of iron 2 sulfate? This is where you're going to get a displacement reaction. The magnesium displaces the iron and forms magnesium sulfate, which is a colourless solution, and iron is formed, which is a grey solid. The iron 2 sulfate is green to start with. Remember, iron 2 ions in solution are green. So green solution goes colourless, or it fades, it gets a lighter green. Heat is going to be released. It's an exothermic reaction, and as I already said, grey solid forms. That's the iron, or it may actually look more like black in the reaction itself. Part 7, state the type of reaction occurring, that is displacement. Or you could also refer to this as a redox reaction.